All right. Well, I will. I'll begin with a word of prayer. So, dear Heavenly Father, we thank you for this day. Again, I thank you for these students. Just ask you just bless our work today. Help us to glorify you in what we do. And we just thank you again, Lord, for your many blessings. In your name I pray, Lord Jesus. Amen. All right. I'll just get straight into it here. So let me just take about 10, probably about 15 minutes to go through the proof of Kepler's laws with you. I want you to appreciate that the proof here is given in terms of, the calculus that you guys are doing. And, well, I think it would be, it'd be pretty, what's the word? It'd be pretty hard to come up with this yourself, right? The stories I've heard is that when the solution to this came out, after Newton published his Principia and everything, there was a time where I think he was kind of censured or something, not allowed to do things publicly. But the solution to this problem came out and everybody's just yeah, that's Newton, because nobody else could do it, Now, in Newton's time, all of this notation, which we currently enjoy, like vectors and stuff, it wasn't around, all right? The notation they had for doing three-dimensional coordinate geometry was really quite different. Honestly, at the point of Newton, real numbers had only been really, in the decimal expansions, real numbers only about 50 years old when Newton did calculus, right? And ideas of algebra, relatively recent in terms of the modern notation. But anyway, so the story goes, Copernicus had He had this heliocentric view of the cosmos, which means what? Sun-centered, right? But then there was a lot of belief in circles. People used to try to explain all of the motion of planets and stars and everything else as circles upon circles upon circles, right? So and if you have a circle and then add another circle to it, if you get enough of these going, you can make all kinds of weird curves. So these are called epicycles. Epicycles have so much flexibility in them, you can fit pretty much any curve. So in terms of its explanatory power, epicycles are amazing. But then the question is that really how the stars and the planets and everything are moving? So then Tycho Brahe took really careful observations over the period of 2 decades. Sorry, my notes are a little bit pixelated. That's Tycho Brahe. And then he died because he drank too much in a drinking contest and wouldn't leave to use the restroom. That's the story, how it goes. And dude also had a metal nose because he lost his nose in a duel or something, or a sword fight. It seems like Tycho Brahe was a bit of a character. Anyway, his acolyte, let's say Kepler, took over and took all of the data which Tycho had been assimilating for 2 decades and sat and looked at it and looked at it and looked at it and found that he could fit ellipses. He could explain where the planets were going in terms of elliptical orbits. And then he had, we would call these Kepler's laws. So Kepler's law that Kepler discovered from just looking at the data, Kepler did not apply laws of physics to derive these. These are empirically determined, all right? The orbit of the planet's elliptical with the sun at a focus. During equal times, this planet sweeps out equal areas, and the period, I know it's hard to see, period squared is proportional to the semi-major axis of the elliptical orbit cubed, all right? And that's it. Now, this is easier to derive if we assume that the sun is at the center, and basically the sun is the center of the sun is the center of mass for the system. That's a simplifying assumption. It makes it so we can go through it in here. The true derivation is a little bit more subtle, but let's stick with this one. So, come on, I said go down. All right. So here's the first. And so this is actually taken from Susan Colley's Vector Calculus, which is a wonderful Calculus 3 book. Unfortunately, we're still of the mindset that we have to attach the Calculus 3 book to the Calculus 1 and Calculus 2 books, which is really unfortunate because, honestly speaking, every calculus series that's known to man, Calculus 3 is an afterthought. The authors put all their time and energy into like Calculus 1 and 2 material. In Calculus 3, it's there. They had to finish it because you got to sell a 3-semester calculus book to schools, right? But their heart is not really in Calculus 3, as is evidenced by the lackluster presentation of things in most books, in my opinion. Now, Susan Colley's Vector Calculus is quite a different thing. It's a good book. Anyway, the motion of the planet lies in a plane which also contains the sun if we assume Newton's universal law of gravitation, which governs the motions through Newton's laws. Let's see how that goes. So if r is the position of the planet and v is the velocity of the planet, what happens when we differentiate the cross product of the position vector and the velocity vector? Well, you guys know we've got the product rule for cross product, right? So how does that work out here? So here we go. d dt of r cross v is dr dt cross v plus r dv dt. But hey, that's v cross v. Well, we know v cross v is 0. So lo and behold, the time derivative of the position cross the velocity is the radius cross the acceleration. All right? Now, in physics, we learned that Newton's second law says what? Newton's second law says that the force is equal to the mass times the acceleration. But Newton's universal law of gravitation says that the force of gravitation is inversely proportional to the distance from the center of the mass of the gravitating object and directed along the line of center connecting the two bodies gravitating, which in our current notation means that it's radial. So the force of gravity is, a formula for it is this, gmm over r squared, r hat. Or if you like to get rid of your unit vectors, you can re-express this as gmm over r cubed r vector, with a minus because it's attractive, and because masses are only positive. So then, what that means is that the formula for acceleration is this. What happens when you plug that back up in here? Well, you've got a constant and then an r, so you're looking again at r cross r, which is 0. That means that this is a constant vector. So the radius cross the velocity is a constant vector. What does that mean? Well, I mean, it means that r cross v is equal to c for some constant, right? So Kepler's first law, the planet's orbit is an ellipse with the sun at one focus. So we've already got this. We're going to use this again. So we take the velocity, we rewrite it. You guys recognize it. It's a different notation, but this is exactly the, oh man. Oh no, we haven't talked about this yet. This is the decomposition of the velocity into the radial part, and this would be the theta hat part, actually, truth be told. But anyway, this is just a product rule, right? dr dt r hat plus r dr dt. Here, both r, the radius, and r hat, the direction of the radial vector, they're functions of time. So when we differentiate, we have to do product rule, all right? Now, if we plug that into our constant vector formula, that gives us c is this, which is that, and then we take the cross product of this, and we get this lovely formula for c, namely r squared r hat cross dr dt. So well, what good does that do us? Well, hang with me here. That brings us to, lo and behold, the acceleration across the constant vector is this. So that's from Newton's second law. This is the thing we just derived in the previous step. So plugging it in there, we get one of these here double cross products. Now the double cross product, we using here the anti-symmetry of the cross product that absorbs the minus, right? I traded the position of this and that. See that? That's a kind of calculation we've learned in here. And then this, well, this is a deeper identity. This is the back cab identity, that the triple product can be replaced with a dot product of a dot product weighted difference of the vectors being crossed. So this is a deeper vector identity, namely this one. Sometimes it's called the back cab identity, because a lot of times you'll see it written with the B first and the C first, and then it becomes back cab. At least that's what it's called in my circle of experience, because that's how the formula appeared in the back cover of the undergraduate book that everybody used to look at the vector identities, namely Griffith's electrodynamics. Anyway, that term is 0 because these are perpendicular, and lo and behold, we just get gm dr hat dt, which this is constants, so we get d dt of that is equal to that. That's equation 2. I always label equations when I'm trying to make part of a larger point, you know? All right, come on. So, continuing, we can derive yet another formula for A cross C, which is namely this. A cross C is actually ddt of V cross C. So put it all together, we've got that A cross C is ddt of this. It's also ddt of that, which then means that V cross C is equal to gm r hat plus d vector, where d is a constant vector. All right? So what that means is that it lies in the orbital plane, since V cross C and r hat do also, right? So see this, this lies in the orbital plane, that lies in the orbital plane, and that means if you have two things in the orbital plane, well, that's also in the orbital plane. All right, so then you use those to set up a coordinate system, kind of like the challenge problem I was telling you guys last time. You define theta to be the angle relative to your d vector and your, come back to me, radial vector, and calculate the dot product of C with C, and lo and behold, putting in all the formulas, we get r gm plus a dr cosine theta. Now you might not recognize that, but that is the equation if we solve for r, and we put z equals to 0 as the equation of this plane. In other words, we're going to set up xy coordinates in the equation of the plane. Well, that gives us this formula, and that, my friends, is the formula for an ellipse, a parabola, or a hyperbola in the plane written in polar coordinates in terms of what's called the eccentricity. You may or may not have worked through that in your calculus too. You almost certainly did not see it in high school, but you should have. You were cheated. Like, this is the full story. Conic sections in polar coordinates looks like this. You're like, well, I took your course and you didn't really do it. Sorry. I spent too long in power series. It's true. It's all true. I'm addicted to power series. I haven't shaken loose of it yet. But and also, I find that the more time I spend on pre-calculus and the calculus sequence, it's the part students have more trouble with. I have less student buyout. Students just give up on my class the more time I spend on algebra. If I took and expanded the first week in vectors here into a month, it would be much worse for you. You want me to be on to differentiation. Just kind of like Calculus 1. Some people take and expand limits into a third of the course. This is madness. Students are not liking that. And it's understandable too, because everybody oh, come on. The double scrolling has gotten me again. Because in your heart, you know you're not going to calculate derivatives with limits after the course, right? You know it's just a preliminary phase of the course, that the real heart of the course is with differentiation and integration, right? All right. I will eventually get back. Come on, come back to me, Kepler's laws. Come back. Ah, this double scrolling, it's evil. All right, so anyway, working through, I just skipped over a couple of the equations, my bad. But if you work through the equations into the xy coordinates, this is the formula that we just were looking at in polar coordinates. It works out to this. At this point, everybody's like, ellipse, right? You got x squared, you got y squared, you're dividing by numbers. And as long as the eccentricity is less than 1, right, you're dividing by positive numbers. That's an ellipse centered at that point, right? Now, if the eccentricity is larger than 1, then I think that makes one of these numbers positive and one of these numbers negative. I think that would make this negative and this positive, right? Because that's squared, so it's positive. If the eccentricity is 1, ooh, well, this derivation doesn't hold there, does it? E equals to 1 would make these equations blow up. Now, eccentricity 1 is the very special case of a parabolic orbit. Eccentricity less than 1 is elliptical orbit. Eccentricity greater than 1 is hyperbolic orbit. So hyperbolic and parabolic orbits are unbounded. You see stuff go past you once, and you don't see it again. It doesn't come back. All right? Elliptical orbits, on the other hand, every so often they come back around, right? And let's see here. Oh, is that? Come on. Then Kepler's second law says equal areas in equal times. So if we want to set up an integral for the area, we can integrate 1/2 r squared d beta. You remember that business last course, the area in terms of polar coordinates. Here I'm using beta for the integration of the polar coordinate. I'm using theta for a fixed meaning. And so if I calculate dA d theta, I differentiate this, but then we've got an integral with a varying bound, so out pops the integrand, 1/2 r squared. And then I can calculate dA dt by the chain rule, and I get this. All right. Now, I think I'm going to relate d theta dt to the, man, this chord is going to get me one of these days. So dr hat dt is related to the d theta hat in this way, if we sort through the details. And now jumping back again to that c vector, we get this, which when I plug in what we just did, we get that, which then ends up giving me the magnitude of the c is actually r squared d theta dt, which then means that dA dt is equal to this, which is equal to that, which is a constant. So the rate of change of angle as you're sweeping through the orbit is a constant. Equal areas, equal times. That's Kepler's second law. And then finally, Kepler's third law is that this t squared is proportional to at cubed, and that you can get from this little derivation here. Of course, the area of an ellipse is pi ab, and so if we integrate, dA is dA dt dt. So of course, the total integral of dA is pi ab, but then we can also characterize that as the integral of the rate of change of area over time, like so, during one period. And when we do that, we get this. But then the thing is, the period is 2 pi ab over c, but remember c, I square both sides, or do I cube both sides? I can't. I don't know. It's anybody's guess. Sorry. I think that's a cube. Is it a square? Oh, it's a square. Okay. I don't have a square to spare. Let's see here. Sorry, it's kind of an irrelevant reference. But t squared is this. And so, oh, there it is. That's Kepler's third law. Now this is the genuinely elliptical derivation. I make my physics students learn Kepler's third law. It's something I test them on. They don't do it like this. You know why? Why do I make it so much simpler in my physics class? What's the difference? Do you remember, Sam? No. At the start, we assume circular motion. So the difference is basically we assume that the center of the sun is the center of mass and stick with that, which then means the motion's actually circular. Motion being circular makes these formulas just that much easier, because you can just basically solve the gravity force is equal to mv squared over r, because the acceleration's totally just center seeking, and that's it. That makes it much easier. So this is the elliptical derivation. There's a better derivation which actually uses what's called Lagrangian mechanics, and you change to something called the center of mass coordinate system, and there's that. This is still a halfway point for the real derivation that you'd learn in your junior level physics course, which we don't currently offer residentially. Sorry. There's an online one you can take in 8 weeks where this won't be derived either, until I take over the course and make videos. But I will not. It's not a good deal. I don't want to teach physics junior level in 8 weeks. You give me that course, you give me 16 weeks, and you let me make 40 hours of videos. At that point, I become interested in teaching that course. Until then, it's hubris. Anyway, do you guys have any questions? We still have tomorrow for homework questions if you got them. We do have one more topic we need to cover, right? Which is what? Integral along a curve. Like, how do you integrate a function along a curve with respect to arc length? It's almost the same calculation as the arc length integral. Arc length integral is just like a special case of this integral where you're integrating the function 1. So if we could do the arc length integrals, we're going to be able to do the integral with respect to arc length. But we'll talk about that integral and its properties tomorrow. But I have time for your homework questions tomorrow too, so, you know. The rest of the time today, though, I think you can probably use for the quiz. So. Anyway, thanks for encouraging me to do Kepler's law. I never do this. So.